Sir, you had told me to ask you about why, like in the primary side, it is taken.
Yes. Okay. So let us discuss that thing first. So open circuit test or no load test is performed on the low voltage side. Okay. Now if we want to perform this test on the high voltage side, then what are the difficulties we may have to face? Let us see that. So let us consider a transformer with rating 10 kVA, 2000 volt by 200 volt. Okay. So if we want to perform this no load test on the HV side, so what are the requirements in that case? Number one, source of 2000 volt, because we have to supply rated voltage. Then we require a voltmeter with range greater than not less than greater than 2000 volt. Okay. Number 3, so let us find the high voltage side current IH, that is 110 into 1000 divided by 2000. Okay, so that is 5 ampere. So this is the rated current, and the exciting current is about 2 to 6% of this 5 ampere. So that is a very small current. So we require one ammeter with very low range. Okay. Now tell me, out of these three, which one are which are easily available? Can you arrange a source with 2000 voltage?
No, sir.
No, sir.
We can arrange, but difficult. Okay. Next, voltmeter with range greater than 2000 volt. It is not possible. Ammeter with very low range. Okay. So 2 to 6% of 5 ampere is very low current. So we require milliampere range ammeter. That is also very difficult. Okay. Very low current. So these are the
Galvanometer is also
difficulties.
not.
Sorry. Mute
Galvan.
yourself, please. Okay, so these are the difficulties we have to face if we want to perform the no load test on the high voltage side. But on the other hand, if we perform this test on low voltage side, then this 200 volt voltage source is easily available. 200 volt voltmeter up to 600 volt, it is easily available. So the voltmeter is not a problem also, and the current rating is 50 ampere, so it's 2 to 6%. That is also a measurable quantity. So ammeter is also not a problem. So that is why we always perform the no load test on low voltage side, not on the high voltage side. Is it clear?
Yes, sir.
Okay. So next is short circuit test, SC test. If we want to perform it on the low voltage side, normally it is performed on the high voltage side. So if we want to perform it on the low voltage side, then what are the requirements? Again, see, first of all, we have to give a very small voltage to circulate rated current. Okay, so source for the same transformer, suppose, so 200 volt, it's 2 to 12%. Source is required. Okay, so that is easily available. So source voltage easily available. Number 2, voltmeter, that is also a measurable quantity, no problem. Now the current, we have to circulate, we have to apply such a voltage that it will circulate the rated current. Okay, now the rated current in the low voltage side, that is we have seen 50 ampere. So 50 ampere, so we have to arrange an auto transformer, that is the supply. We are giving this variable voltage by some auto transformer. So this, we need an auto transformer which will be capable of handling this 50 ampere current. So auto transformer that is not easily available, because handling this 50 ampere current means its power rating, kVA rating will be high. Okay, that is not easily available in the laboratory. Third is 50 ampere current measuring device, that is ammeter, with such high rating, that is also not available. Up to 20 ampere it is easily available. Okay, so ammeter is also not available. Auto transformer and ammeter are the main problem. Okay, so that is why we normally perform this short circuit test on the high voltage side. In case of high voltage side, we have seen the rated current is 5 ampere only. So 5 ampere can easily be measured. 5 ampere rating auto transformer are easily available, and 2 to 12% of 2000 volt, 2 to 12%, that is also easily available, isn't it?
Yes, sir.
So that is why we perform the short circuit test on the high voltage side and not on the low voltage side. Is it clear?
Yes, sir.
Any question? Okay. So let us solve this problem, which is based on open circuit test and short circuit test, which I have discussed in the last class. So here this open circuit test and short circuit test is performed on a transformer with rating 20 kVA, 2500 volt by 250 volt, 50 hertz, and single phase transformer. Okay. So compute the parameters of the approximate equivalent circuit referred to low voltage side and high voltage side. That means you have to find both the equivalent circuits and then draw the equivalent circuit. First of all, you have to find the parameters, then you have to draw the equivalent circuit. Okay. So this is a straightforward question, simple calculation based on the open circuit test data and short circuit test data, and then you have to just refer the quantities to the particular side. Okay, so first of all, write down all the data from open circuit test. These are the data. 250 volt. See, the open circuit test is performed on the low voltage side, whose voltage rating is 250 volt. Okay, 1.4 ampere, that is the exciting current I, and 105 watt, that is the core loss PC. Okay, so no load power factor we can calculate using the formula PC equals to V1 IE cos theta 0. So cos theta 0 is the no load power factor, which can be calculated using the formula PC by V1 I. So calculate this. Hundred five divided by 250 into 1.4.
0.3.
0.3. Find the angle theta 0.
72 degree.
Because we will be requiring this angle to find sin theta 0. So calculate sin theta 0, that is 0.954. If you take the sine of this angle, you will get this. Okay, now calculate IC and IM, the core loss component, and IM using the formula IC equals to I cos theta 0. So I is 1.4 into 0.3. Cos theta 0 is 0.3. So this will be 0.42 ampere, and IC, that is I sin theta 0, (1.4) into 0.954, that is 1.36.
1.36.
Yes. So now we have IC and IM. Now calculate RC, refer to LV side, so L, and calculate XM, refer to LV side, so L. So RCL and XML. RCL is V1 by IC, XML is V1 by XM. So RCL, how much is this?
595.2 ohm.
595 ohm, and XML 187 ohm. Correct?
Yes.
So these are the low voltage side parameters or shunt branch parameters we have determined from the open circuit test. Now consider the short circuit test. So from short circuit test is performed applying 104 volt, 8 ampere, and 320 watt. So 104 is the applied voltage, that is VSC. ISC is the short circuit current or the rated current. Okay, and PSC, that is the copper loss, is 320. Now one thing you have to check, this ISC, if it is the rated current or not. Okay, so you have to check this. So how to check it? So calculate IRH, that is high voltage side current. Short circuit test is performed on the high voltage side. So IRH, rated current of high voltage side, calculate this, 20 into 10 to the power 3 divided by 2500 ampere. Calculate this.
8 ampere.
If it is 8 ampere, then this ISC is equals to IR. Otherwise, you have to calculate this copper loss at rated current by simply applying unitary method. Okay, suppose this test is performed at some other current, not at the rated current, suppose 6 ampere. So in that case, for 6 ampere current, the copper loss is suppose 300. So how much will be the copper loss at 8 ampere current? That you have to calculate. Okay, then you have to follow the same procedure. Okay. So while calculating this short circuit parameters of the equivalent circuit, then first of all you have to check whether the experiment short circuit test is performed at rated current or not. Okay.
Yes, sir.
So ZEH VSC by ISC. So calculate this. 104 divided by 8.
13.
13 ohm. Then calculate REH PSC by ISC square. 320 divided by 8 square.
5.
5 ohm. Now calculate XEH using the formula root over ZEH square minus REH square. So that
12.
will be 12 ohm, I think.
Yes, sir.
So these are the parameters referred to high voltage side, because we have performed this short circuit test on the high voltage side. Now you have to find the parameters referred to first LV side, then HV side. So when when you want to find the approximate equivalent circuit referred to low voltage side, so you have to refer only these two to the low voltage side. When you will be referring the equivalent circuit to the high voltage side, then you have to refer the RCL and XML only. Okay, see, so equivalent circuit parameters referred to low voltage side are these two remain same because these are already calculated from the low voltage side. So refer the high voltage side quantities REH and XCL using the formula, that is REL is equal to REH into turns ratio squared. So you are referring the quantities to the low voltage side, so turns ratio will be 250 by 2500. Okay, so how much is this?
0.05.
0.0.
Okay, similarly calculate XEL.
0.12.
0.12. So now you can draw the equivalent circuit. So this will be your equivalent circuit referred to low voltage side. So you have to write here equivalent circuit referred to low voltage side. Okay,
Yes, sir. Yes, sir.
any doubt? Next, equivalent circuit parameters referred to high voltage side are, you have to refer RCL to the high voltage side. So RCH will be 595 into turns ratio square. Now you are referring to the high voltage side, so turns ratio will be 2500 divided by 250. Okay, so that is why this turns ratio square 2500 by 250 square into RCL, that is 595. So this is 59500 ohm, and XMH is equal to XML into turns ratio square, that will be 18700 ohm, and REH and XEH are already calculated from the short circuit test, which are referred to high voltage side. So now you can draw the phasor diagram, equivalent circuit. Okay, so this equivalent circuit is referred to high voltage side.
Yes, sir.
Any question up to this?
Sir?
Now, if you want to draw, yes.
Sir, when referred to high voltage side, the resistance and inductance means REH and XEH, they should come
Mhm.
first and then the parallel circuit, right?
Not required.
But the
You are
position.
not,
Yeah.
no, see, I have already mentioned at the very beginning of this chapter that there is no such primary or secondary. While you are supplying to the low voltage side and taking output from high voltage side, then low voltage side is the primary side and high voltage side is the secondary side. But when you are giving supply to the high voltage side and taking output from the low voltage side, then high voltage side is the primary side and low voltage side is the out secondary side, isn't it? So here in this circuit, we are considering the high voltage side as the primary side. So you can write 2500 volt here and 250 volt here. Okay. In the previous circuit, you have to write 250 volt here and 2500 volt here. That's all. So in this circuit, the low voltage side is the primary side and high voltage side is the secondary side. But in the next circuit, high voltage side is the primary side and low voltage side is the secondary side. That is the difference. From either side, you can draw the equivalent circuit, no problem.
Yes. Yes, sir.
Just you have to mention in which side it is referred. That is very important. Clear?
Yes, sir.
Okay, any other question? Okay, now if you want to draw the exact equivalent circuit, refer to either high voltage side or low voltage side. So what will you do? Suppose consider this circuit. This is referred to high voltage side. So if you want to draw the exact equivalent circuit, what will you do? Suppose with this question there is another part. Draw the exact equivalent circuit.
Sir, from
Circuit.
REH and XEH, we'll find out R1H and R2H.
Refer to HV side. Then yes, tell me.
Sir, from REH, we will find out R1 and R2.
How?
Sir, REH
So
is
divided
equals
by
to
2.
2 plus R1 into turns ratio square. REH is equals to R1 plus R2 and R2 plus R1 into turns ratio square.
So how will you separate? How will you find R1 and R2?
Sir, I think R1 and R2 both are same equal.
Yes,
So
I have
we will
mentioned
take
it in the last class. R1
Yes,
is
sir, I
equal
will
to
take
R2 equal to REH divided by 2. Similarly, X1 equals to X2 equal to XEH divided by 2. So draw the equivalent circuit, half here, that means this will be the exact equivalent circuit. This is 2.5 and this is 6. This is 6 ohm, this is 2.5 ohm, and these two remain same. This is the exact equivalent circuit referred to high voltage side. That's all. Got it? Okay. Next is calculation of transformer efficiency from open circuit and short circuit test data. Okay. So how to calculate this transformer efficiency from this two test data? we only require the 2 wattmeter readings, nothing else. Okay, so let us see. From open circuit test, core loss equals to PC. From short circuit test, ohmic loss equals to PSC. Now open circuit test is performed at rated voltage. So this PC is rated core loss. Okay, no problem with that. But short circuit test, sometimes it is performed at rated current, but it can be performed at other current also. So this PSC, it may not be the rated copper loss. So you have to check whether it is the rated copper loss or not. Okay, that's what I was telling in the previous problem. So PSC you have to check. Rated VA, that is V2I2, this is the nameplate data. Okay, you will get it from the nameplate of the transformer. So therefore the efficiency can be calculated using the formula. Efficiency at full load is equal to 1 minus sum of the two losses, rated VA from nameplate. Power factor will be given. So rated VA into power factor, that is the output, plus two losses is the input. So 1 minus losses by input. Okay, so using this formula you can calculate efficiency at full load. If the load is not full load but other than full load, suppose at any other load, then you have to multiply this n square here, because this PSC is current dependent load. So current will be current square depends on current square, and here this output is proportional to current only, so 1 n, and here also you have to multiply it by n square. Okay. So using these two formula, or only this one, this is the generalized formula, you can put n equal to 1 for calculating the rated efficiency, I mean the efficiency at rated load, and you can also calculate the efficiency at any other load using this formula, this second one. Okay, and the maximum efficiency occurs when n equals to root over PC by PSC. Both these are rated losses. So PSC at PSC rated core loss, PC rated core loss, PSC rated copper loss. And we know another relation, that is load, KVA load at maximum efficiency is equal to this n into KVA at rated load, that is rated KVA into n will give you the KVA load at maximum efficiency. Okay, any question?
Yes, sir. The last sentence is not clear. Sir, why we are multiplying n? Like
This I have already discussed in the last class.
we'll go through it, sir.
Are you there in that class?
Yeah, yes, sir. Yes, sir. Might have.
So this statement was already discussed in the last class.
Okay, sir.
How this equation we have arrived?
Okay, sir. I'll go through it. Yeah.
No, let me show you, because we are going to apply this formula right now.
Thank you, sir.
See this one. The load current at which the maximum efficiency occurs is given by I2 equals to root over PC by RE2. If we multiply this by rated current, then we get PC by rated copper loss. This is rated copper loss actually. Okay, and this is rated current. Now if we multiply this equation by E2 and divide that by 1000, then we get, this is actually V2 E2 I2, that is the kVA load, I mean VA load, and if you divide that by 1000 you will get kVA load.
kVA.
And this is VA at rated load. IFL is rated current, I2 is some current at which maximum efficiency occurs. Okay, so this is rated VA. So if you divide that by 1000 you will get rated kVA. So from that we can write this equation.
So
kVA,
the n value is this root over thing.
yes. So rated kVA, sorry, kVA at maximum load is equal to rated kVA into, this is actually n.
The constant.
Yes.
Okay.
The load at which maximum efficiency occurs.
Thank you.
Okay, so here another example. This is based on the previous theory, that is how to calculate transformer efficiency based on this test data, open circuit test and short circuit test. Okay, so again we are having this transformer with ratings 10 kVA, 2500 volt by 250 volt, and these are the test data. Open circuit test 250 volt 0.8 ampere 50 watt, and short circuit test 60 volt 3 ampere 45 watt. Now first question is calculate the efficiency at 1/4 load, half load, full load and 1.25 load at 0.8 power factor. Okay, note that power factor is given only without mentioning and it is lagging or leading because it doesn't matter. Okay, calculate the load kVA output at which maximum efficiency occurs. So here you will be requiring that formula, n equal to root over PC by PSC. Okay, and also the value of maximum efficiency. At this load you have to calculate the maximum efficiency also. Okay, so here I will show the calculation of efficiency for one load only, the rest you will do it by yourself. So first of all, from short circuit test we have to check whether it is performed at rated current or not. So full load current on high voltage side is 4 ampere. See, rated current is 4 ampere but the test is performed on 3 ampere. So this 45 watt is not rated copper loss. Okay.
Yes, sir.
So how to calculate the rated copper loss? Just simply apply unitary method. So copper loss at 3 ampere is equal to 45 watt. So therefore full load copper loss is equal to 4 by 3 whole square into 45.
80.
With this formula, is there any doubt or any confusion?
No, sir.
No, sir.
As this copper loss is proportional to current square, so you have to take 4 by 3 whole square. Okay. So this is 80 watt. So now you can apply the formula to calculate efficiency. So, and core loss is given 50 watt, that is rated core loss. So therefore efficiency at 0.8 power factor load at any load is this. So at 1/4 load, this. Just you have to put values of PC, PSC, N, V2I2, that is 10 kVA, which you can write as 10 into 10 to the power 3. Okay. So we need one bracket here. So how much is this? 97.32%. Is it okay with everyone?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
So rest you will calculate half load, full load and 1.25 load. Okay, I am going to part B. Okay,
Yes, sir.
so let the maximum efficiency occurs at n times the rated kVA. Okay, that is, we can apply this formula, n equal to root over PC by PSC. So PC is 50 watt and PSC is 80 watt. So this is equal to 0.79. Okay, now you have to calculate the load kVA output at which maximum efficiency occurs. So now you require that formula. Maximum kVA output, that is equal to n times the rated kVA. kVA at n load is equal to n into kVA rated. This formula. Okay. So that is equal to 7.9 because kVA rated kVA is 10. So 10 into 0.79 is 7.9. Now calculate the efficiency at this load. So again you have to apply the same formula, putting n equal to 0.79. Okay. So here also you need one bracket. So how much is this?
$98.44.
Yes. So 98.44% is the maximum efficiency. So please calculate the efficiencies at other loads and check whether it is higher than this or not. As we are claiming that this is the maximum efficiency, so you must check. Okay.
Yes, sir.
Yes, sir.
Any question?
No, sir.
Yes, sir.
Okay, next we have also mentioned that using the short circuit test data we can calculate the voltage regulation. Okay, so let us check whether it is possible or not. So this problem is based on voltage regulation from short circuit test data. Okay, so here a short circuit test when performed on the high voltage side of a 10 kVA 2000 volt 400 volt single phase transformer gave the following data. So this is short circuit test data. Now if the low voltage side is delivering full load or rated current at 0.8 power factor lagging at 400 volt, find the voltage applied to HV side. Okay, so first tell me which one is primary side and which one is secondary side.
High voltage side is the primary.
Yes, because load is connected to the low voltage side. Okay, Now see, these are the rated voltage, and we have seen that rated voltage means E1 and E2. Okay, now the load is voltage across the load is 400 volt, that means V2 is 400 volt. Okay, so here load power factor is lagging, it is already mentioned, so this E2 has to be greater than V2, so E2 will be more than 400 volt. Okay, now to get E2 greater than 400 volt, we have to apply a voltage in the primary side which is more than 2000 volt. So how much is that voltage? We have to find that. Is it clear? So how to find that? We can find that by calculating the change in terminal voltage. So for that we need RE2 and XE2, that we can calculate from the short circuit test data. So once we get this, we will be able to calculate E2 minus V2. We know this from the voltage regulation calculation. So let us see. So given parameters are short circuit current ISC is 4 ampere. You can check whether it is rated current or not.
No, sir. Rated current is 5 ampere.
Yes, but as we are not calculating efficiency, so it doesn't matter. Okay, so whatever may be the short circuit current, we can calculate the voltage regulation on that basis. Okay, based on short circuit current, that is okay. So short circuit current ISC is 4 ampere, supply voltage is VSC equals to 60 volt. Therefore copper loss at this short circuit current is 100 watt. So based on this, the high voltage side parameters are REH is equal to PSC by ISC whole square. So how much is this? 100 by 4 square, which is 6.025.
0.25, yes, sir. So 6.25.
Is it?
Yes, sir.
Maybe. Okay, so this is 6.25. Next, calculate XEH, ZEH, VSC by ISC.
15.
Calculate XEH, root over ZEH square minus REH square.
$13.63.
13.61 ohm. So once we get REH and XEH, we can find the parameters referred to low voltage side. Now why we would require this? See, short circuit test is performed on the high voltage side, but that is the low voltage, that is the primary side for this transformer, but load is connected to the low voltage side, which is the secondary side, and we know we have to find E2 minus V2, which is equal to I2R RE2 cos theta 0 plus I2R XE2 sin theta 0. sorry, not theta 0, theta 2 actually, sine theta 2. So we require the secondary side parameter, which is low voltage side here. That is why we have to refer these parameters. Okay, so 6.25, this will be 2.25 into this trans ratio square. So calculate this.
0.25.
And XCAL.
Zero 0.54.
544. Yes.
Okay, now calculate full load secondary current, that is 25 ampere.
25.
10,000 divided by 400, which is 25 ampere. So that is the secondary rated current. And now E2 minus V2 equals to 2 I2L, that is the rated current, that is I2R, into RE2, that is REL here, because the low voltage side is the secondary side, cos theta 2, and for lagging power factor this will be positive. So I2L XCL sin theta 2. Okay, so for cos theta 2 value of 0.8, you will have sin theta 2 equals to 0.6. So
0.6.
put all those values and tell me what is the final value for E2 minus 13.16 volt.
Yes.
Yes. Now calculate E2. V2 is given 400 volt, because here see, low voltage side is supplying some load at 0.8 power factor lag at 400 volt. Okay, so the output voltage V2 is 400 volt. For that, what will be the value of induced EMF in the secondary side or low voltage side, that is E2. So calculate E2, that is 400.
13.16.
Yes. Now using the trans ratio, calculate the supply voltage to the primary side. So the primary applied voltage will be this into trans
So
ratio.
2065.8.
Yes. And if you are asked to calculate the voltage regulation, then what will be the voltage regulation?
65.8 by 2000 into 100.
Sorry. Repeat. Voltage regulation equals to what? What is the formula? E2 minus V2 by E2. So here E2 minus V2 is 13.16 and E2 is 413.
0.0063.
So calculate this, whatever. Is it clear? Any question? So that means if you want to maintain 400 volt across the load terminal with this given load at 0.8 power factor lagging, then you have to apply a voltage across the high voltage terminals, that is this voltage 2065.8 volt. Then you will be able to maintain this voltage. Okay.
Yes, sir.
Okay, time is over. So to up to this.